Yes, as Bob just mentioned, I had an issue two weeks ago, and unfortunately, I wasn't able to make it in person today. But I really appreciate the invitation to present at the BIF. That would be my first time in person, but now it's my first time online. And I really would like to thank everybody at the BIF team for helping to accommodate this presentation in an online format. And everybody that is sitting there, thanks for your patience to do this not in person, but online. So the study that I'm presenting today, this has been conducted by my master's student, Luana Alvarez. And to start, I'd like to mention our motivations for this study. So horned flies is one of the most common summer pests for cattle that can be found in most of the countries, the cattle producing countries in the world. So there is no doubt that these blood-sucking flies, they are annoying and really harmful to cattle, and they make a real burden on livestock operations. So the stress caused by horned flies infestation that can lead to physiological responses, including elevated heart and respiratory rates, which may impact also the metabolic rate. And that is due and also reducing the amount of energy for production. Indeed, there are several studies that have shown the impaired growth rates, milk production, and also feed efficiency in herds that are not controlled for horned flies. This can be partially explained by the fact that some animals, the animals engage in several avoidance behaviors, such as tail flicking, leg stumps, head throws, which result in decreased grazing time. Horned flies have also been suggested as vector of some pathogens, and I'm going to talk more about this later on in my presentation. On top of that, we also have that the production intensification has exacerbated the horned fly problem due to unplanned and usually uncontrolled use of insecticides. On top of that, flies are developing resistance to current available chemicals, and the current solutions that we have, such as ear tags or topical insecticides, they're not as effective as they used to be in the past. In terms of the puron formulations for insecticides, they can also contaminate the animal's dung, and as a result, it can kill large numbers of beetles and flies associated to the dung of the cattle dung. And these insects, they might play a role in the natural incorporation of the dung in the soil, which is an important process in the terms of maintenance of soil fertility. When we look to the consumers, everybody all the time we are seeing these, that the consumers are looking for practices that are more environmentally friendly, and that would include also the reduction of the chemical use, and that also contributes to limiting the producer's choices for fly control. In terms of economic impact, if we combine the expenses and losses due to horned fly infestation in cattle, it is estimated to be over $1 billion per year. And although these numbers might be shocking and it seems pretty high, I would say that it's pretty that might be underestimated, especially when we consider that cow-calf operations in the southeastern and middle west of the United States, where cattle spend significant portion of their lives on pasture. And on these states, we have an extended summer season, which maximize cattle exposure to horned flies. You might be wondering how we can differentiate horned flies from the other common flies. One way it's how is their mouths, how they feed themselves. So house flies and face flies, they are non-biting flies, while the stable and horned flies, they are biting flies. That's not easy because we need to look at the flies or be sure that they are biting or not. So if we want to differentiate the ones that are biting, that are the stable and the horn flies, there's a pretty easy way to differentiate them. And that is based on their feeding position. So when feeding, the horn flies are usually in a head downward position, while the stable flies, they are in their hosts, and we are going to see them in a head upward position. So that's pretty easy. It's just to see when they are laying the animal, which position they are, head upward or head downward. We will know which fly that represent. Another important difference is that the stable flies, they usually stay in the animals only during the day, and they are in the animals just while they are feeding. And while the horn flies, they stay in the host all day long. So more about the biology of horn flies. Males and females, they're obligated blood feeders, and that means that they spend most of their adult life on the host. So the females are the ones that are going to leave the host, but just for a short period of time, and they do that to deposit her eggs on fresh manure. Usually she's going to deposit around 20 eggs during each visit, and she may lay up to 400 eggs during their lifetime. So the hornfly eggs can hatch as little as 11 hours after ovulation. These larvae will initiate the pupae phase within 3 to 5 days, and the pupae period ranges from 5 to 7 days. It means that the total period from egg to the adult to emerge, to the adult emergency, ranges from 9 to 12 days. It's a pretty short life cycle. In terms of number of generations per year, it really varies broadly and varies with the climate. For example, cool temperate regions, we might see from 6 to 9 generations per year, while on warm and subtropical zones, we can expect from 12 to 14 generations per year. A really extreme example is the northeastern of Brazil, where 30 generations were documented in a single year. And that's due a life cycle of 7 to 11 days. So in regions like that one, for example, what happens that we are going to see horn flies consistently infesting the cattle year round. Soon after the adult emergency, so the horn fly is going to search for a host, and then the cycle restarts. In terms of feeding behavior, the hornfly mouth parts are adapted for skin piercing and blood sucking, and they are intermittent feeders, and they fed as many as 20 to 40 times per day. In terms of blood meal size, it varies between animals and males and females, with the females ingesting, in average, more blood than males, and for a longer a day. The blood meal acquisition, it's necessary for horn flies for survival, sexual maturity, and also egg production. In terms of behavior, so as I mentioned before, the horn flies, they remain day and night on the host. They rest in feeding on part of the animals that they cannot reach easily with their head or tail. You might see that usually in the cold parts of the day, the horn flies are going to cluster on the cattle's back, side, and withers. But during the hottest hours of the day, they are going to migrate to the animal's belly. So that's all that I'm going to talk about in terms of biology of horn flies. So let's talk about their impact, no? So horn flies are key pests in cattle, especially in cattle under pasture conditions. The infestation can cause direct and also indirect effect on animals. The direct effects are observed on animals' behavior, health, and performance. There is extensive literature talking about how it impacts animals, also showing that in yearling steers and heifers, which were treated or were controlled for horn flies, animals could gain up to 18 to 14% more weight, respectively, compared to uncontrolled animals. When we look at the literature, the effect of fly infestation in cattle in terms of impact of on pregnancy rate, postpartum interval, days to pregnancy, and calving interval, this has not been yet proven. The indirect effects of horn fly also have been reported since 1996, so pretty long time ago. And this study shows that calves paired with insecticide-treated cows, they have an increase in average daily gain and also an increase in the weighting and the weaning weight. And the better performance of the animals with horn fly control compared to those that didn't receive any control for flies, that might be explained again by changes in their behavior, of the animals that are infested. So the change, especially in grazing patterns. As I mentioned earlier, flies can cause stress in the animals in making the animals display some defensive behaviors to avoid flies. And I'm sure that everybody that is sat there knows what are those behaviors. No, wagging tails, shaking the head, stomping, rippling their skins. That's all the animals can do to get rid of the flies. And these behaviors, they have a negative influence on the health and also the performance of the animal, as it decreases not only the feeding time, but also the resting time of the animals. These two studies that I have listed there, they look at the activity of yearling steers that were treated or untreated for fly control, and comparing these two groups of animals, what they found is that the untreated animals, they spend more time walking, probably because they were really annoyed with the flies, and they consumed less grass at time, they ruminate more, and they also chewed each bolus fewer times and for a shorter period of time. So all these changes in animals' activity and behavior may explain the reduction in weight gain, and that is due to not only altered grazing patterns, but also additional energy expenditure to avoid flies. No? In terms of horn flies' impact on host health, so horn flies are known as a vector of Staphylococcus aureus, that is a bacteria that causes mastitis. So as we know, mastitis is an inflammation of the cow's mammary gland. It's often considered a disease of dairy cattle, and because of that, it's often overlooked in beef cattle. However, when beef heifers are under development, the levels of estrogen and progesterone, they increase, and so does the irritation from horn flies. So if the infection occurs while the heifer's mammary gland is still under development, so the extensive damage can be caused in this tissue, resulting that the heifer is never going to be able to reach her genetic milk potential. So therefore, the mastitis, if it happens in beef cattle, for example, that's the one that we are working with, it can have an indirect impact on calves' performance by decreasing their growth rates due to impaired milk production of their moms. I also mentioned that horn flies can be vector not only of the mastitis, but from other pathogens. In a pretty old study mentioned that horn flies were also an intermediate host of Staphylococcus stilesis, which is a nematode that causes a granular dermatitis that occurs primarily in the belly, scrotum, and other of cattle. And it was pretty common in the west and southwest of the United States. So these lesions, that are caused by the dermatitis, increase the susceptibility to other infections and also may reduce the price of the hide in the market. No. More recent studies have suggested that hornflies as a vector of bovine leukemia virus, which is a disease that is responsible for the development of lymphosarcomas. And you might know that this is the single largest cause of carcass condemnations in the United States, totaling about 13% of beef cattle carcasses and 27% of dairy cattle carcass condemnations in the US. So pretty important disease that could be transmitted by horn flies as well. So I hope that at this point I convinced you the importance of horn flies in beef cattle and in cattle in general. So you might be wondering, how can we evaluate fly infestation? No? So the most traditional way is visual observation. If we want a more precise phenotype, in the beginning was suggested to do direct count of flies on the animals. You can imagine how demanding and labor intense is this process, no? Which really limited its large scale application in terms of having enough records for a breed association, for example, to include this trait in their genetic evaluation. And I'm sure that most of us, we are not willing to collect these records. So as an alternative, a scoring system that varies from 1 to 5 was suggested, but the main problem here is the definition of the thresholds for each score. That might vary from one herd to another, from one region to another, and even depending on what's the animal category that we are evaluating. So having these scores is kind of complicated in terms of there is a subjective evaluation as well. It's hard to differentiate if the animal have 200 or 300 flies. So how am I going to classify that based just on looking at the animals? So more recently, with the development of digital techniques, what we see is some research groups are proposing to use image analysis for counting flies. So the idea is to use video recordings or even photographs, and based on these images, counting flies in the computer. There are other research groups, not only ours, that are working on these and try to develop an automated tool to process images and counting flies. But I would say that it's in its early stages of development. For hornfly control methods, for sure, each of you have a different method that have seen or have been using, or alternative ones. So we have chemical ones, no chemicals, and some no traditional methods that have been proposed. Some of them have been widely implemented for hornfly control. I would say the most common ones are the purons and the ear tags with insecticides. I'm not a specialist in fly management planning, so I will not make any recommendation today on how to define or implement effective fly control. For that, I really recommend to talk to a specialist or a veterinarian. What I want to draw your attention here is that one of the non-traditional methods is the selection of resistant animals. It would be great if we could have an additional tool to our arsenal to deal with horn flies that are animals more resistant or less susceptible to flies. And that could be an alternative to the conventional chemical control. In terms of factors that have been reported to be associated with cattle attractiveness to horn flies, there is a vast literature on that. Studies have shown that, for example, breed is an effect, and Bosinicus are more resistant than Bostaurus animals. Also, the body size, the hair density, coat color, males are more susceptible than females, and other factors related to blood clotting proteins and immune-related predispositions. However, these factors don't entirely explain the differences in abundance of horn flies across and within breeds. So we really believe that there is more factors and genetically related factors that are unknown yet. So previous studies have shown that Yes, there is a genetic component, and just like the attractiveness to mosquitoes in humans. So you might be the person that, when it's outside, the mosquitoes just like you or love you. I'm the one like this, but you might be like a person as well that, the mosquito never come to you. So there is something that attracts or repels mosquitoes, similar to what happened with horny flies in cattle. So there is a variability from one individual to another, which indicates that there is a genetic component underlying it. There are several studies that suggested that and suggest that the selection for horny fly resistance could provide a long-term solution for this complex problem. However, the accuracy of this approach relies on having high quality and large-scale data collection, which is quite challenging and labor-intense to collect. When we look to heritability estimates in the literature, has a pretty wide range. It goes from 10 to 80%, which indicates the impact of small sample sizes, maybe potential lack of uniformity in data collection or subjective assessment or phenotype, and also the absence of clear trait definition. Those could be some reasons for this wide range of heritability estimates. So as a consequence, it clouds really our ability to dissect the genetic basis of resistance to horny flies in cattle. So with all this information in mind, we started this study in 2021, collecting horny fly load records and several other records at the UF multi-breed Angus Brahma beef cattle herd. So the University of Florida multi-breed herd, beef cattle herd, it represents a kind of unique resource to understand the genetic basis of horny fly resistance in cattle. This is a crossbred population that include animals with all breed compositions between 100% pure Brahma to all way 100% pure Angus. All animals are pasture raised, and they are all submitted to the same management conditions, which makes this population a really good resource to investigate the genetic resistance to horny flies in cattle. So far, we have 748 multi-breed calves with records and genotypes for 250,000 SNPs. So in this specific herd, animals are classified into breed groups from 1 to 5, which are determined based on the percentage of Brahma breed. So in this table, you can see the number of animals with records per breed composition in our study population. And in this plot, we have just the number of males and females across all the 5 breed groups. And as you can see, it's quite balanced in the number of males and females evaluated in our data set. The first thing that we did was to take a look in the genetic diversity. So using a principal component analysis, we saw that the PC1 explained over 35% of the genetic variation in our population. And it clearly represents the variation due to breed composition, we also see that in this plot, great genetic variation. And as expected, we see a gradual separation between the breed groups 1 and 5. Remember, the breed group 1, represented here by the black dots, those are the animals with the highest Angus percentage. And the breed group 5, represented by the light blue dots, those are the animals with the highest percentage of Brahma. So we see both are in their extremes, and then we have the crossbred animals all the way in between these two groups. So overall, this analysis demonstrated how breeds are segregating in our population, and also the importance to control for population structure in our analysis. Given the diverse breed composition and also the genetic variation in our animals, we have a great variability in terms of coat colors. So we identified 3 different categories of coat color. We call dark, that represented the animals brown and dark and black. Then we have the color that are kind of reddish coat colors, and the light that goes from white, beige, and tab coat colors. And in the plot below, you can see the coat color distribution by breed group. As expected, most or the vast majority of the animals in the breed group 1, those are the animals with the highest percentage of Angus, they have dark coat color, with just few exceptions, and that is because we have animals in this group that may have up to 20% of the Brahma breed. And the other extreme, the vast majority of the animals in the group 5, those have light coat color with just few exceptions, again, because in this group, breed group 5, we have up to 20% of Angus breed in these animals. We look at the skin color of the animals, and the skin color was determined by the color of the skin around the animal's eyes, and we have these animals classified into two groups, dark and light. So dark, it included the brown, again, variations between black and brown, and the light is going to be kind of white or pink skin color. So black is by far the most common skin color, regardless of the breed composition. We also see few animals that have the light skin color, and those are animals that lack some pigmentation, you know? So it's the low frequency that we observed in our population is less than 6% of the data. It's not a surprise because animals are selected against this trait due to photosensibilization issues that might lead, for example, to cancer eye in cattle. So in terms of the phenotype, definition, how we define our resistance to hornfly phenotype, that's based on image analysis, and we use the fly load as a proxy for resistance to hornflies. Keep in mind that lower infestation indicate higher resistance, okay? For that, we use images extracted from video recordings made with a GoPro camera mounted on the top of the squeeze chute, and we analyze those images using the software ImageJ. Our fly count is performed almost manually, as the software just assists on totaling the number of selected positions on each image. So the final phenotype is determined as the average of fly count from 5 images per animal. And we do these evaluations at weaning, and that's for two main reasons. The first one, our herds, there is no fly control on calves from birth to weaning. And the second reason is that weaning is performed from August to September. So in this case, we hope we are avoiding some potential confounding effects due to residual insecticides, and also it maximizes the animal's exposure to hornflies during the summer season, allowing the animals to really express their full genetic potential for attractiveness or resistance to hornflies. With this data in hand, the first approach that we did was to test the influence of breed composition, skin color, coat color, and other factors on fly load. So for that, we used the transformed natural log value of fly count because the raw counts were not normally distributed. So looking at the results, we have here this first plot that showed the distribution of fly count per breed. And it really confirms the previous finds in other studies that higher the proportion of Brahma breed, lower is the susceptibility to hornflies. And in terms of when we do the mean comparison results, what we see is that animals with more than 40% Brahma breed, those animals that belongs to the groups 3, 4, and 5, they have significantly lower fly counts when compared to animals from the breed group 1 and 2, that are the animals with the highest percentage of Angus breed. In addition, when we look at the two extremes, the mean fly load for the high Brahma percentage animals was 51% lower than the high Angus percentage animals. So these results really emphasize that there are differences in attractiveness to hornflies between Bos indicus and Bos taurus cattle, but so far the genetic mechanisms that drives this difference has yet to be determined. Coat color was also significantly associated with susceptibility to horn flies. There is a good variability in terms of fly infestation observed between the different coat colors. As previously reported, darker coat colors are more susceptible to horn flies than lighter colors. And also our results corroborates with visual orientation of many Diptera fly species that usually they search for darker animal form and they have a certain inability to see the red color. In terms of sex and the skin color, both of them, we didn't detect any significant effect on the fly load. We can see here the distribution of fly count for males and females. Despite the great variability in both categories, the average fly load is pretty similar between them. And it's pretty similar also what we observe, the behavior that we observe for the skin color. So there is greater variability in fly count for the animals with dark skin color, but the average was pretty close to the animals with light skin color. So that's why we didn't detect any statistical difference between these two skin color categories. So our next step in this study was to determine the feasibility of genetic selection and also investigate genomic regions associated with resistance to horn flies. For that, we fitted an animal mixed model under a GBLUP method to estimate heritability and breeding values. The analyses were performed using the BLUP-F90, and for this analysis, we used 721 animals and over 124,000 SNPs. Based on our data, the heritability estimated is 30%. And it indicates that there is a great genetic variability in the resistance to horn flies, and genetic selection for cattle resistance to horn flies is feasible. Here I have the representation of the breeding values for all animals that we had in our population, and it ranged from minus 1.45 to plus 1. That demonstrates that some animals in our population, they have greater genetic resistance than others. Note that in this case, positive values represent high fly load. That means animals genetically more susceptible to horn flies. And we are interested in selecting animals with negative breeding values. And here we have the representation of the breeding values by breed group, with higher percentage Brahma animals showing greater genetic resistance than higher percentage Angus animals. Why is that? So that is where we are right now. We are trying to understand the genetic mechanisms controlling this trait. Before I go, the last result that I want to show you is this GWAS analysis that we just performed. You might be familiar with this. So the peaks represented the regions that are associated with the resistance to horn flies. We set a threshold of 1% of the genetic variability to decide if a SNP was significantly associated with the trait or not. But I want to bring your attention for these three regions. In the chromosome 18, for example, the genes located in this region, they have been reported to be associated with physiological adaptation to environmental stressors, including infectious disease, extended drought periods. It pretty relates with animals, bosinicus animals, and where they were selected. That might be a reason of these regions showing there. The regions in the chromosome 19 and 29, they have been reported to play a role in the immune system. We need to dig more to understand what would be the association with resistance to horn flies. But curiously, on the chromosome 29, the gene that's the TMEM225 gene, that gene has been associated with resistance to malaria. And malaria is a disease transmitted by a mosquito. And that was, it's curious to see that, a disease associated with mosquito, we are talking about horn flies, and we got the same gene here. So it's not clear for us yet what the mechanism or the biological mechanism that would be underlying that, but we are working on that. So before I go, I just want to give you some take-home messages. There, for sure, I hope that I convinced you at this time, if you're not convinced yet, that hornfly infestation is a real issue in the beef cattle operations. The current solutions are not as effective as they used to be, and their efficiency tend to decline due to fly resistance to chemicals. Public concern is knocking on our door in terms of animal welfare, environmental impact that requires novel management tools, especially in reducing the number of chemicals that we use in livestock productions. We are really excited that our preliminary results captured the variability between and also within breeds. We also observed that not only breed composition, but coat color influence cattle resistance to horn flies. And there is a genetic component. We want now to further understand what are the mechanisms that are underlying it. This study wouldn't be possible without the involvement of many and many people. So I'm really thankful to all my current and former students and visitors that have helped collecting and processing all these images, and also the UF farm managers and staff for their support to this research. Thank you for your attention, and I'll be glad to take your questions.
Thank you. I'm not sure this mic is working. Do we have any questions? One thing I'm wondering about, you've at least convinced me that the horn flies are important, but how do we get enough measurements to do an evaluation? Any ideas?
So what we are doing right now, we have 700 times 5 is 3,500 images. So that were analyzed and counted flies. What we want to do, what we are working now is to see if we can develop like artificial intelligence, software that we just going to be able to recognize flies in images. So that would be a way that we can implement that in a large scale, So that's what we are working.
Okay.
About the phenotype, so you're counting all flies, correct? Or the image is able to differentiate specifically the horn flies? Or is it effective? So, thank you for the presentation, Fernanda. My question is, you're counting all the flies, or the camera is able to differentiate specifically the horn flies? So my next question would be, is it a fair assumption that the resistance for flies is like for all flies are the same?
Did you hear that?
Really bad. She asked about differentiate, but I can't understand. I couldn't understand what is the differentiate what?
Can you differentiate between different fly species?
Oh, no. So right now, with the image, it's possible. No, I just assume because we look at the animals from the top, so in the shoot, so we are assuming that those are horn flies. So I cannot tell if they are really horn flies or if they are, stable flies, for example. So no. It's pretty hard to see them, especially when we have Angus animals that are dark. It's really, it's complicated.
From here, you can translate it for me? Don't try. Okay. So basically, my question is, she's looking at Brahmin or light versus black. So within a population, let's say Brahmins or Angus, what would she expect the variability to be for consistency? That makes sense, Bob?
Yeah, I think so. So crossbreeds,
Yeah.
what's the variation in resistance amongst the fly population?
Yeah, we know the Brahmins are probably more resistant than Angus, but within Angus.
Oh, gotcha. Within the cattle, not the flies. I mean,
Within 100% of the meat.
yeah, so Fernanda, the question is, do we expect about the same amount of variation in resistance within Brahmin as we would in, say, Angus, or vice versa?
Great question. So we do have data in purebred Brahma. It's not too many. We have 400 animals evaluated now. And I don't have this question because, we are still working the images, but I don't know if within Brahma. So when you look this plot, let me go back because that might tell you there is variability, no? So we can see in this, it's not pure Brahma. I cannot say that's a pure Angus or pure Brahma, but those are the extremes. And we see variability within each breed group. So my expectation is that there is variability. We can find, a really resistant Angus animal and a really resistant or a really susceptible Brahma animal. So yeah, I do expect to have variability within breeds as well.
And from that plot, can you pull out the 100% of each from each extreme?
I could, but then I have just few animals. It's hard to infer about that, But yeah, I do. I do have animals that they are 100% Angus and 100% Brahma in these groups, in the extreme groups. I do have it.
Just not enough to really tell him.
No, not enough. Not now.
Anything else? So let's thank Fernanda one more time.
Thank you, guys.